Welcome back to another episode of Peep, an EIP focus series, where we have an overview of a proposal and try to understand why that is needed for the Ethereum mainnet. Today, our guest is Kelly Olson, and the EIP for discussion is EIP-2565, repricing of EIP-198 Mod EXP precompiled. The EIP-2565 is a standard track core EIP, which is in the last call status. It was proposed in March this year and has been discussed in few all core dev meetings. This is also being considered for the upcoming Berlin upgrade. Welcome to the show, Kelly. Please let our audience know a little bit about yourself and your engagement with Ethereum chain, and then we'll dive into the presentation.
Yeah, sure. Sounds great. So my name is Kelly Olson, and I've been, somewhat involved in the Ethereum community really since its launch. Most recently, I've started working at a company called Supranational that focuses on hardware acceleration of some of these new cryptographic primitives. And that's one of the reasons sort of why we started looking into repricing this EIP-198 proposal, is that there's a number of these new cryptographic techniques that are coming out that can help scale Ethereum with things like, zero knowledge rollups and what have you. And so the goal of this EIP is really just to make those things more affordable and to better reflect the cost of their operations, and match the gas price to that. So I can go ahead and share my screen and maybe give a little bit more of an information on this EIP. Okay, great. So just to start, as Pooja mentioned, this EIP is repricing a previous EIP, EIP-198. And EIP-198 introduces a new precompile for modular exponentiation. And for those that aren't familiar with precompiles, these are essentially specific functions that are too inefficient to run inside of the EVM. And so special code has to be written for them so that they can execute sort of natively on your platform with bespoke code that's written in and implemented in the client. This function in particular is modular exponentiation, which is used in a wide variety of cryptographic algorithms. And it was, this precompile was originally proposed by Vitalik to allow for efficient RSA signature verification. So the RSA signature scheme is highly dependent on these sort of modular exponentiation operations, but they extend sort of well beyond that. And really the ultimate goal of this EIP is to, a number of things have changed over the past, 3 or 4 years since this EIP was originally implemented. And what we found is that the original estimates for how to price the EIP could be improved upon to sort of bring them in line with the costs of other EIPs. So just as I mentioned before, this is a foundational arithmetic operation. So most of cryptography relies on these sort of modular operations, whether that be modular addition or modular subtraction or what have you. And in order to verify some of these more advanced cryptographic functions like snarks or accumulators or verifiable delay functions, you have to do these modular exponentiation operations to check that the proof that is sent to you is actually valid. And unfortunately today, while it is possible to verify things like snarks and VDFs and accumulators in the EVM with this precompile, it's very expensive. So it can cost, upwards of, 2, 3, 4 million gas, depending on exactly what sort of proof you want to verify. And so this makes it very, basically expensive, especially with recent gas prices. This could be $30 or $40 to do one of these functions in the EVM. And so, sort of with this in mind and given that Ethereum is looking to move forward with using more of these cryptographic techniques, we wanted to make sure that that cost was really justified, or whether, perhaps it could be optimized. So the sort of very first thing that we went out and did in this EIP is we went and did a benchmark. So every EIP and every precompile has a set of test vectors and a benchmark that you can run for these test vectors. And so what you'll see here on in sort of this first column is we've got EC recover, which is one of the main precompiles that's used today, and it's an elliptic key recovery. And then we have a whole bunch of these test vectors for the modular exponentiation precompile operation. And really the main thing to call out here is that currently the pricing for other precompiles like EC Recover is about 20 million gas per second. So this means basically if you submit a transaction and it takes 1 second to verify, you'll be charged 20 million gas. And that's sort of the standard pricing metric that's used across the EVM and also with the precompiles, is really trying to target this amount of gas. So when we go look at the current gas pricing and the execution time for these other precompiles, or for the ModX test vectors, what we'll see is that the gas pricing is anywhere from about 100 million gas per second all the way up to about 550 million gas per second. And what this means is that when you call this precompile in the EVM, you're going to pay anywhere from 5 to 20 times more than other precompiles are paying, right? And so this was a great discovery for us, because we said, hey, great, these things cost maybe $40 or $50 now, but they're unfairly priced. They're too expensive for how quickly this operation can be done. And one of the main reasons why it may be too expensive is really just these cryptographic libraries that are used by the clients have gotten better over time. So they're able to put in better algorithms. Computers have gotten faster in the past 5 years. And so while, the pricing originally was maybe, more reflective of what it was at the time, now when we run these things with better algorithms and faster processors, they don't take as long, and therefore they shouldn't cost as much. So that's really the core idea behind this EIP. Is we did some benchmarking. We found that it costs about 5 to 20 times more what other precompiles are costing. And we said, okay, well, let's go bring these costs back in line with these other precompiles. The second thing that we did is also look at how these precompiles are priced and how the gas is assessed. So in the original EIP-198 proposal by Vitalik, which I can share here, what this proposal does is it tries to estimate how long these modular exponentiation operations are going to take to run on a computer by looking at the underlying algorithm that the implementations were using at that time. And so in this case, as Vitalik calls out, this function is intended to approximate the difficulty of something called Karatsuba multiplication, which is one of the techniques and one of the algorithms that's used by these libraries to do this function. Well, what we found is that over time, more and more of these libraries have actually evolved to use a more efficient function. And so what we were able to do is, rather than using this formula that Vitalik had described here that represents Karatsuba multiplication, we were able to modify this formula to better represent the algorithms that are actually being used today. And what we did here is we ultimately took these test vectors that are already part of the precompile, and we priced them with the old pricing formula, and we priced them with the new formula. And ideally, what you would want to see is sort of this one-to-one comparison that as the complexity goes up of the pricing formula, so does the execution time. And you'll see that Vitalik's original estimate was a fairly good estimate, right? So for at least these sizes that we're looking at, he had an R-squared value of about 71.71 or 71%. What we found, though, is that by actually, specifying this new complexity formula to better, represent the actual algorithm that was used, we were able to bump this up to about 92%. And what this means now is that the gas pricing formula is a better predictor of the actual time that it's going to take to run on your computer. And that's really what ultimately we want to do when we're pricing these gas precompiles. So maybe I'll just pause there. That's kind of the very high level overview of what we're trying to do in this EIP. We're trying to make its cost similar to the other costs that happen in the EVM or that happen in other precompiles. And then 2, we want to make the gas pricing formula as accurate as possible so that everything is priced more fairly. So maybe I'll pause there and just see if Pooja or Alita have any questions.
I just have a comment here. I remember when this EIP was introduced in the all-quarter meeting, people were like really happy to see the kind of benchmarking it was done, and in my knowledge, for the first time, it was also mentioned as one of the EIPs that could be that many other EIPs can follow as best practices. So yeah, thank you for this great work.
Yeah, absolutely. And I think, one of the key, components of that is just, all of the client developers have a lot of issues on their plate, right? They're getting a number of EIPs. I'm sure there's, 10 or 20 new EIPs that are submitted every week. And so it's really important that you come as prepared as possible into these EIP meetings. And so, I can maybe just show briefly, we did a whole bunch of work originally in the spreadsheet where we looked at what were the original benchmarks, why was it priced this way originally? And we went through a lot of trial and error in understanding exactly, why the original estimation was not as good of a predictor of the computational costs as we thought it would be, right? And so I think the best thing to do is the more information you can bring into that EIP process up front, it's really helpful to sort of move it forward. So, just as a quick example, we looked at what are the original benchmarks when the EIP was originally implemented. We went and benchmarked a whole bunch of libraries to understand, are these implementations today good? Could they be better? We looked at different ways to reprice it and how could we get, sort of a better fit with these different algorithms. And so I think, in general, I do know that a lot of the EIPs come in a little bit half-baked sometimes. And so I think, it's really useful if folks can do as much due diligence as possible before coming in so that the client teams, have those questions answered and the process can move forward quickly.
So I have a question. Do you mind walking through here and explaining, I guess sort of as trivially as possible, what exactly is happening, like what these dots are on the graph, for example?
Yeah, absolutely. So at the end of the day, the whole point of gas is is something that you're paying for computational time, right? So when somebody gets a block off from the network, they have to process that block and make sure it's valid before the next block comes. So you have a very limited amount of time to process these blocks. And gas is one way to ensure that, if a block is coming every 15 seconds, gas ensures that it doesn't take 45 seconds or a minute to actually verify the block. So what you want to happen is that gas is closely tied, and the gas pricing is closely tied to the time it takes to execute on the computer. So what each one of these dots is a look at the gas price, either according to the old formula, which is in blue, or the new formula, which is in red, as compared to the execution time. So as a very, sort of trivial example, here is something where the gas price with the old formula would have said that this should be, 10 million gas, but the new formula said it should only be, 100,000, right? So even though they both took the exact same amount of time to execute, one formula was a better predictor of its execution time.
And
so that's ultimately, yeah.
And so are you saying that when, for example, when I send an instruction set to a miner or to something to compute it, I'm giving it a certain amount of gas, and then it's saying, okay, I'm going to use this formula, which is the presumably currently the blue trend line. And
Yep.
If the execution time is above presumably the intercept there on that line, then I will say that it is underpaid and therefore cancel the execution. Is that correct?
It's close, but the prices are sort of fixed. So, in the client, when you get a transaction and it's got a few instructions, you look up what that should cost. And that's all based off of previous EIPs. So you may get a transaction and you say it uses these 3 precompiles and the total cost is 1 million. Now, whether that takes a half a second or 10 minutes, you're still going to process that transaction. So it's really, the sort of gas cost is hard fixed up front. And that's why it's so important to determine accurate pricing up front.
And so right now, then, the current determination is overvalued, meaning that when you are going to compute the, I forget exactly what it's called, but I think it was the modular exponentiation precompile, then the formula currently is going to say, I should give you presumably about, whatever magnitude amount more than you should be getting in terms of the gas price to actually compute that.
Exactly. Yeah. So the long and short is that what's hard coded into the clients is they charge you too much, right? They charge you as if you're spending a minute worth of computation time, but you're really only spending 1 second because of these better algorithms and better processors. And so the whole goal here is, the collective users of this precompile are all getting overcharged, right? Unfairly, you could say, right? And so the goal of this is to say, hey, you shouldn't be charging us 1 million, you should be charging us 100,000. That's
okay.
The key point here.
So I think we have sort of, to not go off topic, I think we should continue and maybe try to get through the rest of the slide, because I think up to this point, it's pretty clear what the problem is and what the solution is.
Perfect. Great. So let's just dig right into the EIP as it stands today. So as we mentioned, really the motivation here is to bring the precompile in line with all of the other costs on Ethereum, other precompiles and operations in the EVM. The current formula is in EIP-198 is specified with sort of 3 main variables. It has this multiplication complexity formula, which tries to determine how big of a multiplication you have to do. It has this adjusted exponent length variable, which determines how many multiplications you have to do. And then it's got this, what they call the G-quad divisor, which is really just a way to normalize that with the rest of the other gas prices. So this is just a simple parameter that you can move up and down to bring this in line with the current prices. So the first thing that we recommended in the EIP is to replace the original multiplication complexity formula with the simplified one. And the simplified one is what gives you, sort of this better fit here, right? So when we use the simplified formula versus the one that Vitalik had originally done, we get a better estimate of the gas costs. So that's the first recommendation of the EIP.
And just let me quickly, sorry, when you say a better, I just want to say one thing. With that line, it's under the assumption that different jobs might take different amount of times, but on average, the general price will be equivalent to what is actually being used. Is that correct?
Sorry, could you maybe say that one more time?
Sure. So, for example, you have the red dots, right? And you have a couple dots that are off the line because this is the best fit linear curve. And I'm wondering here, this gas price formula is not built to be exact for every single computation, but rather on average.
Yes, that's exactly right. And what I would say is rather than even exactly average, it's more that we target the worst case. So what we actually do in this EIP is we know that, for instance, some of these ones are maybe underpriced. We're going to just shift this line by modifying this G-quad divisor to ensure that nothing is underpriced. Because the last thing you want to do in Ethereum is have something that's underpriced, because then that means it's potentially a denial of service vector. Someone could submit a whole bunch of these transactions that are all underpriced, and it takes someone an hour to validate it. So this trend line sort of gets us the formula that's right. And then what we're going to do with this G-quad divisor is just sort of move it down a little bit to make sure that everything is either priced accurately or overpriced, but just less overpriced than it would have been, basically.
And that's a really great point that I think we should come back to later. So again, try not to go off topic, but because I remember during the all-core devs meeting, there was a discussion about clients worried about that very vector of denial of service vector. So we can come back to that same explanation later. Sorry, didn't mean to interrupt you.
No, it's a great question. I think it's a very important thing for folks to be thinking about. Okay, so as we mentioned, we sort of we modify this multiplication complexity formula from the original one in 198 to this new function. This moves us from sort of the blue line to the red line from that previous thing. The second thing that we do is we update this value of G quad divisor. So before, we knew it was overpriced, and this had a different value. So we just changed this value so that we are getting close to that 20 million gas per second. And then the last thing, again, just to address this denial of service precompile, what we found is when we looked at the original EIP-198 spec is that there were some very small values that actually were underpriced, like very, very small values that probably no one would ever use, but they were underpriced. And so what we do with this last update is just say, no matter what, if you call this function, you're going to pay at least 200 gas. And this is, again, just to make sure that nothing is underpriced, because we don't want any denial of service vectors here. So that's really the whole specification. We basically update one value to 3. We put a maximum of 200, and we also change this complexity formula.
Maybe
it is a it's a minimum of 200. Exactly. If when you sort of type it up into Python, you say take the max of this or 200. So, but yes, it is a minimum of 200. That's correct. The rationale, I think, we've already sort of talked about before. We had this current complexity function. We realized we could make a better one that uses, is more in line with how clients are actually doing these operations. With this G quad divisor, we said, hey, we're going to move it down. So, maybe just to speak a little bit to your point, we wanted to make sure if this 20 million gas per second is fair pricing, right? We have a straight, one-to-one correlation here with execution time and gas price. We want to make sure that any of these dots are always over this line. And that what that means is it means that we're never underpricing any of these. And so the very key thing, I guess, maybe to take away and understand this graphic is, this is fair pricing, the yellow line. This is what pricing was before, and we're trying to move it somewhere in between the two. So it's cheaper than it was, but it's still not presenting a denial of service vector because it's more expensive than the completely fair pricing. That's really the takeaway. And so the benefit is that you do get cheaper pricing than it was before, but you're not introducing any new risk to the system because you're ensuring that it's always taking at least that 20 million gas per second price. Maybe the last thing just to talk briefly about is, these test cases, right? So there was an original set of test cases. The clients are going to go implement these 3 changes that we talked about. And so they need to make sure that, the 4 different clients or maybe more that are out there, that they're all in sync, right? So we need to make sure they're all getting the same answer once they update it. And so what we did is we updated the test vectors. So we said, before they all agreed that when you ran this test vector, you should get 204 gas as the answer. Now they should get 200. And you can really see the net reduction. Here's a test vector that used to cost 285,000 gas, and now it only costs 87,000. And this is really, this is the whole of why we did this, is that everybody's going to get it's going to be about 4 times cheaper than it would have been before. So that's the long and short of sort of the EIP walkthrough. So it's fairly simple, but certainly a lot of work goes into it to make sure that you're not presenting or adding any risk into the ecosystem.
It definitely requires a lot of background checking. Thank you very much for your work on this. It's a very impactful change to the gas calculations.
Yeah, absolutely. So maybe just to summarize, this is what the new EIP pricing looks like, right? So before, if you remember, we had some things that were up to 500 million gas per second, right? Well, once we implement the new pricing formulas, those changes we recommended, you'll see that all of these test vectors are over the 21 million gas per second, but they're substantially lower than they were before. So something that used to be 500 million gas is now only 165 million, right? And this is really the net of the change, is that everything is much closer to this fair pricing here. So what's the status of this EIP? So benchmarks have been conducted for both Geth and Open Ethereum. We did a performance analysis to basically figure out what the right new pricing formula was that balanced the cost reduction that we wanted to see with the denial of service prevention that we needed to have. We have draft implementation in Geth and Open Ethereum. And we also have the EIP in last call status, which should be moving to final here in the next week or so. So what are some of the learnings? I think the first one is, engage as early as possible with the client developers to get their feedback on the proposal. So, when we originally went in with this EIP, we sort of had a range of options and said, these are some different ways that we can tackle the problem. And it was really, informative to get that feedback from the various developers so that we could craft a proposal that was going to be acceptable to them. Anytime when you're doing gas pricing, it's not sufficient to just look at one client. And we had a ton of struggles here and a lot of time spent because for whatever reason, the library and the function that Open Ethereum was using was much worse performance than the one that Geth was using. And so, you need to ensure that you don't prevent or, create a denial of service for one client, right? Because what could happen is if Geth or, Open Ethereum was really slow, someone could spam a bunch of these transactions. The Geth nodes are fine. They'll proceed with life because they're fast. But the Open Ethereum ones all get, kicked offline or unsynced or, lag behind on the head of the chain. So it's really important to, not just look at Geth, but to also look at the other clients because client diversity is, sort of a goal of the Ethereum ecosystem. In general, this 20 million gas per second is what you want to be targeting for when you're setting gas. It's the rough area, but you want to shoot for this in the worst case scenario, right? So, in our case, we did have one that got down to 28 million, right? And so this is where we said, okay, we're going to pause. We're not going to reduce this any further because in the worst case scenario, it could be at this 20 million and we don't want anything underpriced, as we mentioned before. I guess the last couple things, ideally, when you submit the EIP, as I mentioned, the client teams are very busy. There's multiple clients that are going to have to upgrade. So if you can minimize that implementation complexity as much as possible, that's great. One of our original EIP proposals was much simpler. It was, hey, instead of this number being 20, change it to 200. It was literally a 1-character change that would have got us a 10x improvement. But unfortunately, that didn't work for Open Ethereum. But that would have been the ideal case, right? Is that you make it that simple that the clients go in, they press one button or they add, one line of code and you've made the change. Sometimes libraries do need to be changed for clients. In the case of Open Ethereum was much slower than Geth. If they do need to change and you want to help Open Ethereum or a client determine what library to use, it's really important that you understand what their requirements are. So we did a lot of work on benchmarking for Open Ethereum, but at the end of the day, they said, oh, we don't want to use this library because it's tough to build on Windows. So that was a requirement that they had. And so we said, okay, let's go find another library or let's change the pricing formula to make sure it works. And then the last piece I'll say here is, gas pricing is a bit of an art. We're trying to get everything, to be priced at least 20 million gas per second, but not much more, right? So that it's fair. But, to price this, you really need to understand what is the hardware doing underneath it? What are the algorithms doing? What is like the actual CPU doing? Those will help you come up with better formulas if you actually understand how this gets executed to get those better pricing formulas. And that's what we were able to do with this EIP is we knew what algorithms, libraries we were using. We knew how the multipliers actually work in the CPU. And so that's really important. And, last but not least, the number one priority here is to be conservative with the pricing to prevent denial of service risk. So, selfishly, everyone would like gas to be as cheap as possible, and nobody wants to pay gas or transaction fees. But it's important that the network is secure, and so number one priority is really make sure you're not introducing new risk into the ecosystem. So, tentative plan, in terms of next steps, the EIP will move to final status this month. The EIP still needs to be implemented in Besu and Nethermind. We'll then test this in a multi-client testnet, likely YOLO v3. It'll get implemented on a normal test it like Goerli or Ropsten or what have you. And then hopefully in the Berlin hard fork, this repricing will actually come to mainnet and people start to see the benefits of the improved pricing formula and the lower cost for these operations. And that is, I guess, the conclusion, but happy to answer any questions that you may have.
Thank you for this. So I have a question on the benchmarking and on the client implementation side. I remember in one of the all core dev meetings, it was mentioned that Geth has asked for some rework, and that I think would be considered for the consideration of this particular proposal for the V3. So do we have anything on that? I mean, like.
Yeah, that's a great question. So the most recent all core devs call is that Geth had said, we've implemented this. It looks good from our perspective, but we need to know that it's good for Besu and Nethermind, right? So that what we've done is since we've reached out to both of those teams, the Besu and Nethermind team, we've said, hey, could you run the benchmark? And then we can make sure that, again, it's 20 million gas per second or more for all of these test vectors. So the hope is that we get that at the latest before the next all core devs call, but ideally, we would get that, sometime, in the next couple of days.
Great. Do you mind I think that pretty succinctly covers the whole EIP. Do you think there's anything else that was sort of not covered or as, I guess, trivially as possible? Do you think, is there anything else that you would like to clear up a bit?
No, I think that's about it. I mean, I think, just the only comment would be, moving forward for folks, certainly make sure you're engaging with all of the different development teams and that you're, constantly getting that feedback and refining the proposal. And yeah, that's what it takes to move forward.
Great. Now, do you mind if I ask a couple off-topic questions, like, I guess, about the future or whatever else? So one interesting thing to me that I saw while watching this was this idea that you're overcompensating. So the price for a certain precompile, for example, would be always greater than or equal to the slowest client in an ideal world. So a faster client then is going to have more bang for their buck in terms of accepting those orders because it'll take them a shorter amount of time and they'll be paid as if it was taking them longer. Is that correct?
So all clients will sort of, they're all going to pay the same gas price. So what it really means is if let's say Geth is faster than Open Ethereum, it just means that Geth is going to complete validating that transaction before the Open Ethereum one. All nodes have to process all transactions. So you're going to pay the cost. You're always going to pay the same cost, right? For whoever processes the transaction, whatever miner processes it. So yeah, it really just means that, faster clients are faster. They're going to use less computer resources. They're going to finish the transactions quicker, that sort of thing. The goal is that all clients can keep up, which is why we price them so that even the slowest one can keep up with the chain. But some clients will just naturally be faster. And all that means is that they're going to finish validating these transactions quicker. It does mean that it's going to be more overpriced on those clients, right? Like if for instance, Open Ethereum didn't exist, we could make this precompile probably twice as cheap. But unfortunately, fortunately or unfortunately, depending on the way you look at it, Open Ethereum exists. We want them to stay synced with the main chain. And so we need to make sure they can process these transactions. And therefore we need to charge more because they are slower.
So I guess the thing that's really interesting to me, for example, is this sort of microeconomics of the way that Ethereum works in terms of the miners and their incentive to perform. So in other words, what I'm trying to say is that with this set gas price, it's interesting because if you're at the highest level, or as you just described, it might be overpriced. And so therefore new clients or in the future clients are encouraged and incentivized to produce something that can perform that computation more quickly so that they can do more and therefore earn more money. And that's an interesting sort of like leveling ecosystem.
Right. Yeah, that's the one thing I'll say is that you can't earn more money because there is a gas limit in Ethereum, right? So even if a Geth node could process twice as many transactions, they can't include more than 12 million worth of gas in a block. So it's kind of unfortunate because you sort of you have this situation where you're only as fast as your weakest link in Ethereum, and if you're faster, it doesn't get you anything really. Like, I mean, it makes your node run faster, it uses less computer resources, that's great, but you don't make any more money, unfortunately, because the Ethereum protocol caps the total number of gas that can be used in each block. And today that number is like 12.5 million or something like that.
That seems like a missed opportunity, but very interesting. Thank you for explaining.
Yeah.
All right, well, Pooja, I think I'm good. I don't have any burning questions, unfortunately. Thank you so much, Kelly.
Yeah, absolutely. It's my pleasure.
Yeah, I think this presentation is really good. We can now wrap up the discussion. I'm hopeful for this proposal to make it to the YOLO V3 version and ultimately to the Berlin upgrade. Thank you, Kelly, for joining us, and also to Alita for helping us understand the proposal better with your questions. For people watching us on YouTube, you can contact Kelly on Twitter, Kelly M. Olson. The contact for the author and rest of the crew members of this meeting are mentioned in the description box below, along with the presentation shared. We will also provide the link to the proposal. If you have any questions, comments, or concerns about this particular proposal or any other, please feel free to leave a comment. Let us know which proposal you would like to see next in this series. We need your love and support. Do like, share, and subscribe to the Ethereum Cat Herders channel, and let other community members know about the Peep and series. See you next time with another proposal. Till then, this is your host, Pooja Ranjan, signing off. Take care.
Thank you.
Thanks so much, Pooja.
Thank you.